So I'll talk about the evaluation of FRP retrofitted structure under seismic loading. So I come from CSTB, which is an evaluation national, let's say, company that evaluates new construction products. First, I will present the CSTB and the technical assessment of construction products. Then I will focus my speech on RCFRP retrofitting for several use, including seismic. And then I'll talk about open issues and ongoing research at CSTB for seismic technical assessment. So first, the CSTB was founded just after the Second World War in order to prevent low quality reconstruction building. And its aim was to produce the assessment of new construction products. That's the public goal of CSTB. Then we have developed our goals in order to have some certification to verify that the characteristics of products remains the same over time. Then we disseminate knowledge, and then we do some research in order to do assessment of new construction products, etc. For the technical assessments of construction products, we look at several criteria. Some are usual for the type of presentation that we have seen. For example, the adaptability to the intended use or the conformity with the regulation. Some are unusual. We have the integration inside the building, we have the maintenance, the durability, and the safety, of course. We do this kind of technical evaluation through models, calculation, and testings. We have a lot of scale 1 testing device, both for fire mechanical, cold mechanics, or hot mechanics, and also for fumes and stuff like that. Then when we have all this data, there is an approval of the product intended use that goes through validated scope of use of the new product through a peer review that's called the Groupe Spécialisé. It's an expert committee, and anyone can join this expert committee. And then there is an open diffusion to the stakeholders, and that's something that is called an AVI technique, and it's open source on the CSTB website. Now we'll focus on RCFRP technical assessments, focusing on the scope of use, the one that we call, let's say, usual, and the one that are unusual. And then I'll talk about the technical assessment for RCFRP, including seismic aspects, and then I will have a seismic focus. For the scope of use, what we call usual is when we have some extra loads to an existing building. That's, let's say, the statistical case. It's mainly linked to modification of building use, and also we have some reinforcement of existing masonry building. That's what we call the usual scope of this type of FRP structures. We have some unusual scope, for example, reinforcement and waterproofing. Then the FRP is implemented in the intrados of the structure, and it has also a use for waterproofing of buildings. And also seismic retrofitting. That's what we consider as the National Technical Evaluation Committee as an unusual scope. Regarding the technical assessment, firstly, we look at, for all FRP, including seismic applications, we look at the perfect scope of use. Thanks to the IFGC recommendation guide, there are some material characterization testings that are validated throughout the scientific committee, and also validating design model. That's what we call the perfect scope of use. Then we look at the graded scope of use, that's the second step of the evaluation, the graded or damaged scope of use. For example, we have incomplete bond surface, initially cracked concrete, slightly deviated FRP, etc. Let's say that a lot of studies show that in order to have a good characteristics for FRP, we need to have a very precise way to apply the FRP on the existing structure. We look at product characteristics that can be done by non-experts people, So the degraded scope of use is very important for us. We also have the integration in the building. It can be, for example, retrofitting strategy for the same FRP to RC ratio. You can have one large layer of FRP or some small layers. It doesn't have the same behavior with regard to the building characteristics, especially for seismic application. We look also at temperature, depending on the north of France, the south of France, or other areas or other application. Here you have a chimney where you have very high temperature. You can have a behavior that is really not the same. We have also some specific exposure or unusual aggression. That's what we look at when we do an evaluation of new products. And finally, we look at the capacity for insurance. That's, let's say, one of the most important goals of AVI technique is for your structure to be insured in the end. And insurance look only at repair capacity and costs with regard to the mitigation of existing risk and, on the contrary, increase of damage risks. For example, leakage inside building. When you have the anchorage, we look at the fact that there is no extra leakage possibility when we implement new FRP products. And also adaptability to building modification when you need to have an opening in a building. That happens sometimes. We look at the possibility for the FRP that has been implemented to deal with new openings, for example. Now, a specific focus for seismic application. The context is that we have an increasing demand for FRP, RCFRP products for seismic assessment. However, up to date, no AVI technique has been established for this scope of use. The context is particular. We have some milestones that have been accomplished, thanks to Emmanuel mainly, and the team of AFGC. We have two guides considering the, let's say, the perfect scope of use that I've shown you. There are some remaining milestones. The one is a coordination with regard to other evaluation services throughout the world in order to have, let's say, a common basis of evaluation. Then we also have one specific aspect for seismic analysis. The product is done locally, whereas the behavior for seismic application is global. So when you do a reinforcement locally, we only evaluate the capacity locally, but the seismic application is really global, so you don't need to, you need to address the change in the eigen frequency of the building, the eigen modes, for example, the failure modes. We have to look at this very precisely when we look at reinforcement for this particular application. So we need to develop models and methodology to transfer from the product scale to the building scale, and also testing protocols, because we mainly look at scale 1 testing. So the presentation that we have seen this morning is very important for us to see how it behaves and how we can come from the product scale to the building scale. It's really important. Now, open issues and ongoing research done at CSTB. I have one for static capacity and one for the dynamic behavior, or two for dynamic behaviors. For static capacity, we've done a study for RC beams with different type of reinforced FRP. One on the one side at the bottom of the beam, one on two sides, both at the bottom and at the top. And here you can look at the normal effort, and here the momentum that is applied on the beam. You can see in blue the RC beam. It's the classical curve that you usually see. With one side FRP, you have a reinforcement here, even though you don't have any normal effort applied to your beam. And with two sides, well, it's symmetrical almost. Because here we consider classical rebars, so you have more rebars at the bottom than at the top, usually for this type of structure. Here is something that we usually see for, let's say, old building. You don't have any rebars at the top. And here is the classical behavior that you have for the same type of beams with no rebars at the top. You can see here the reinforcement only on one side and here on two sides. we just focus on the momentum capacity, not on the shear capacity or at the connection between a beam and columns. Here we've done the same for columns, also the same for just for momentum. Here we only look at two sides reinforcements because there's no interest in looking at only one side reinforced. And then this is the perfect static analysis. Now here is some kind of degraded application that we can look at. Here we have a classical beam, and we use an initial strain impact. So when you apply your FRP on your beam, there's an initial effort that is applied on your beam. Most of the time it's a momentum. And here we have looked at different initial strain linked to initial stress. So we consider here 60% of the maximum momentum for the classical RC beam. And we have here a decrease in the momentum capacity that is not that much. And when we are just at the limits of the momentum capacity of the classical RC beam, when we apply the FRP, there is a very large decrease of the momentum capacity of the FRP because of the press strain that we have at the moment where we implement the FRP. So depending on the building that we have and its initial strain, we have a very large variation just for static application on the momentum capacity, the extra momentum capacity that is addressed by the FRP. Now we look at dynamic influence. First one is let's say the eigenmode modification. Usually it's an increase in stiffness in the structure, but also a change in the stiffness behavior because the cracks happen not at the usual time that we are used to. We have some elastic behavior and non-elastic behaviors. Here the aim is to see if there is a positive or a negative impact on the eigenfrequency and eigenmodes throughout the building when we implement an FRP reinforcement. The goal of this research is to have analytical determination of the eigenmode. It's really important for this to be analytical in order to know exactly for different shapes, different types of reinforcement, how it will change both the frequency and the shape of the eigenmodes, mostly the first eigenmodes. Here is an example that we have done for holes inside orthotropic slabs, and we are dealing with orthotropic patch on orthotropic plates in order to address this kind of stuff. And then we want to integrate it through, for example, substructuration to the global building behavior, not only at the wall or slab level, but at the whole building. And also to have, let's say, a decision advisory tools for FRP retrofitting strategy in order to address and assess the new FRP products for seismic, let's say, goal. Then we have also the failure mode modification. That's something that has been said a lot during the different presentation. Usually you have strong columns and weak beams, and you want to reinforce your structure, reinforce the weak point, but you don't want the reinforcement to deal with weak columns, otherwise it's, let's say, decrease the capacity, the overall capacity of your building. So what is very difficult here is that we need to address a product for every type of building, not one, not two, but every type of buildings. And we need to, let's say, focus on a building database in order to address the impacts of FRP reinforcement on the overall behavior of building. We've been focusing on the EMS 98 building types. That's something that has been done for pushover analysis, for example. We need to establish another database for, let's say, FRP seismic reinforcement use. Then we need to determine the chain of failure, for example, through pushover method, with and without FRP retrofitting, and identify good practices and, let's say, wrong practices in order to specifically address this point on the AVI technique of FRP products. Well, I thank you for your attention. And if you have any questions.
Thank you very much. We have time for questions or comments. Any questions? Yes, please.
So first of all, we have to thank you to come to discuss with us, because for us the CSTB point of view is very important, because as you know, we need technical approval to develop these techniques. So my question is, I think, very simple, but we had a quick discussion yesterday and I'm not sure to have understood your response. So what do you need now to give technical approval about seismic strengthening by FRP?
That's a very good question and very tough question. If I just, well, the approval process is kind of complex in France because the CSTB is the approval body, but we are only instructing and looking at the documents that are provided by the people producing the FRP. And then it's presented to a group spécialisé. So there is a peer review, and that's the group spécialisé that takes the decision to make an assessment or not. The CSTB is only here to have a neutral point of view, and also to give exactly the same type of evaluation for every people that comes with a new product with the same type of scope of use. So since it's the new seismic, the seismic application is a new domain for technical approval, it's very difficult to answer your questions. Let's say that the points that I've been listing on my presentation are some aspects that will be looked at by CSTB. It can be addressed either by models, calculation, or testing. Most of the time, testing are, let's say, have a higher influence on the decision, the technical decision, than models and calculations. But both can be done. Then what is difficult is that I cannot have the point of view of the group spécialisé beforehand. There are some possibility to have smaller groups of experts that give an extra list of things that are required for the technical assessment, and then in the end it's only the group spécialisé that has the decision. Let's say that this is the minimum list of the points that will be checked for new FRP products. I'm sorry for this not very specific answer. I think the main part is the link between the product scale to the building scale. It's very difficult and tough, and I guess most of the people that have done the presentation this morning, you can see that when you come from only one section between a beam and a column, and when you go to a building scale, it's very difficult to anticipate the behavior. And here we have to address the impact on the building, and there's a regulation that says that we cannot downgrade a building when we try to upgrade it. So we have to match this regulation, and it's very difficult to address.
Any other comments or questions? Towards the end of your presentation, you talked about databases, building databases with regard to failure modes. What exactly are you referring to? Are these are you referring to experimental results, or to analytical modeling, or to real case studies?
Well, looking, let's say, at everything at the same time.
Everything at the same time.
Most of the time it's an, let's say, an agreed database, agreed by the group spécialisé. to say that this type of building is representative of, let's say, 25% of the construction in France, or 20% of the construction in France. And so if we address this type of products to this specific type of building, then we have a good analysis to, let's say, this type of building can be reinforced by FRP. So we need to have a database that is both a numerical database, so that we can implement that in different calculation codes, for example, or just analytical ones for using Eurocode 8 methodology, for example. It has been done in the past, but I guess it will be difficult now.
Yeah. Okay, well, thanks a lot. Thank you very much.